Hello, everyone. Welcome back to Perceive 2021. Please give a warm welcome to our very distinguished guest, Josh Tabor. It's a great honor to introduce Josh because he's our staff software engineer and joined us from Google and system have been instrumental in building Clarifai stack. So Josh will be talking about Flare, which is our AI platform. So welcome to our stage.
Thank you, Yu-Chen. So we're very excited to tell you about Flare, which is our new Edge offering. You know and love api.clarifai.com. Flare brings much of the power of api.clarifai.com, our cloud API, to the edge. And that can mean a lot of different things, as you'll see. So one thing that we think differentiates our Edge platform from others is flexibility and composability. We think of our Edge platform as an extension of Clarifai in the cloud. That means that models that you can use in the cloud can be synced to our Edge platform. That means that the same API that you're familiar with from the cloud can be used on our Edge devices. And while none of this tethers you to the cloud, of course, our Edge offering can be used without access to the cloud at all. This does allow you to do a lot of your configuration on Clarifai.com and bring down all that you've built to your Edge devices. We have built our platform on top of Kubernetes and Helm with the intent of creating a very resilient, self-healing deployment. We target multiple different architectures. We'll talk a bit more about that later in the presentation. And we have quite a few use cases in mind, both smaller devices and what we would call a thicker edge use case as well. And we've put a lot of work into making sure that we have the best models for you to build on top of. And we are working to build the most performant and flexible video platform. You can see two videos with detections from a person vehicle model that was run on our Edge platform. One of these was actually recorded on an NVIDIA Xavier AGX device, and the other was recorded on a different deployment. But you can see on the one, at least in the top right-hand corner, there's not just detections, there's tracking, and there's quite a lot of flexibility. You do not have to do tracking like this. Pretty much anything that you can do in our platform, you can bring to the edge. To that point, we kind of imagine quite a few use cases. This is really just the start of our list. Whether it's manufacturing and detecting defects, quality control. There's a large predictive maintenance use case as we see it. Retail and pattern analysis, consumer behavior in stores, as well as defense and emergency response use cases. So all of this is great, but there's some challenges that come with deploying AI to the edge. And I think that some of these are apparent. People often talk about model footprint and frame rate, but unfortunately, there's more to this story. Actually, there's a lot more to this story. So you have to deal with not just having a fast model, but deploying that model. And fleet management, making sure that you have up-to-date versions of your platform running on many different devices. Model iteration is probably the biggest. the whole model lifecycle, all of the challenges that come with deploying in a regular environment or deploying in a non-edge environment, building a model on api.clarifai.com still exist on the edge. You still need to label data, refine models, iterate on models, evaluate how we're doing, and just having a highly optimized way of deploying models doesn't necessarily fill in those gaps. We also need a good way of collecting training data, and to that point, we would actually love to be able to get data from the devices, because one of the biggest problems is that the training domain will differ from what we would call the deployment domain. Oftentimes, the final solution will involve several different models put together, and might involve composing some sort of detector with some sort of tracking, and perhaps also some transfer learned component on top of that to detect some custom concept space that's different from what the detector was trained on. So also being able to compose multiple models together is a very important component. And I guess if this wasn't already obvious, in order to label lots of data, get lots of data, there is a human workforce component to it. Basically, all of the same challenges that you encounter now will exist on the edge. And just to kind of better articulate this point, take a screenshot from a model that is not doing well. In this case, you see this is a person vehicle detection, much like we saw in the aerial footage before. But here it's being applied into a very different domain than what it was trained on. This was trained on aerial footage, and we see this being used on much lower altitude footage, or a picture from street level. And you see lots of spurious detections here. In fact, it thinks that this woman's wallet is a vehicle, and we clearly need to do much better. So this is an example of where we would maybe, if we had the right training data, if we could collect data from the devices, we could iterate on this model, or iterate through other models that might apply better to this type of situation. Thankfully, Clarifai attempts to address practically every single part of model lifecycle and an AI deployment lifecycle. So we think that we can really address all of these problems. So of course, there is the frame rate and model size problem. We start with these state-of-the-art edge optimized models. There's we allow you to sync the models from our platform. So that is part of the deployment story. Another part of the deployment story, actually deploying the Clarifai stack, we'll talk a little bit more about whenever we talk about the architecture. We hope to make that as easy as everything else. There's an integration with NVIDIA Fleet Command. Many people use that for fleet management. But beyond that, we can talk a bit about all of the tools that we have in the Clarifai cloud. So for example, our scribe tool that you see in the Clarifai portal for labeling data, and our labeling as a service label force can help, are very powerful tools for annotating your data. We have a wonderful interface for training and evaluating models, both transfer learn models, which we support on Edge, and deep train models. We will be supporting some more Edge optimized templates soon, but even in the interim, you can bring in your own models and evaluate them as well through our model import functionality. We have workflows that allow you to compose multiple models, and very importantly, we have built into the Clarifai platform and built into our Edge offering collectors, which allow us to sample the real-world predictions that are happening on the device. Obviously, on the edge, this happens a little bit differently since the devices are not always connected or perhaps rarely connected. But collectors allow us to buffer and, when possible, flush that data if you choose to so configure it to the platform so that you can label the actual, you can label images that are actually from the deployed domain. And once you rebuild or iterate on your workflow in the Clarifai platform, you can sync it. And finally, of course, Clarifai helps many companies build and iterate on their models, and we can help you build your edge solution. So a bit about our architecture. First and foremost, we started with what we run in the cloud. Obviously, we don't run the exact same stack from the cloud on the edge, but we do bring the entire, or at least very large portions of our API. So the same interface that you use for predictions and workflow predicts, you can use on device. We chose to build on top of Kubernetes and Helm because Kubernetes has a lot of self-healing aspects to it and allows us to, when appropriate, scale up and down deployments. Not everything is a thin edge device. In some cases, the edge might mean deploying to a thick server where we can scale up multiple instances of our inferencer, and Kubernetes allows us the flexibility to compose our platform in that way. And it also allows us to bring some of the very powerful components that we run in the cloud down to the device. We are delivering as much as possible for the supported devices, single command bootstrapping, so that we'll set up everything, starting with a device that has none of the dependencies, neither Kubernetes, Docker, etc., installed, to bootstrapping a device that has the Clarifai stack up and running on it. We support right now x86 and ARM, and we have started to work on specific device support. Our first two devices that we're supporting are NVIDIA Xavier AGX and NX, but more will be coming down the pipe. Of course, as we discussed, the models are bootstrapped by syncing them. We've thus far talked about syncing models from Clarifai, but we've built a flexible architecture that lets you sync models from arbitrary locations. Not every edge device is intended to ever be connected to the internet. Some of them will only have the benefit of files that are local to their local file system, or perhaps served within some company intranet. So even if model files can only be delivered to the device, we can sync those files into the platform. So a unified model and workflow syncing framework, so that whether you're syncing from api.clarifai.com or files that have been manually exported for your air-gapped environment, we provide some unified framework by which the devices can be configured. And finally, an edge or any deployment can only truly be validated if you can monitor and log it. And we optionally, per configuration, allow you to pipe logs out of the device. So let's take a deeper look at our architecture. Pull up a diagram here. this is a very rough, high-level sketch of some of the components. So on the left-hand side of the screen, you can see my pointer. This is basically, or at least this portion, represents our installation on the device. This will be what we run in Kubernetes. Each of these boxes represents another process, not necessarily a single process, but a process that we're running. And we sync with the cloud. The root of the request tree is this Flare API component. This public-facing process, or this process that provides our API interface, is built from the same process that we run in the cloud that provides the logical termination of users' requests. Now, of course, we are not just taking the cloud deployment. There's many changes, many things have been pruned or optimized to the edge, but nonetheless, we can run a scaled down version where we provide the same external interface to the world. Images get passed through our a somewhat similar, although pruned stack that decomposes the images, samples them, and passes them to various backends to run the models. An important part of the story, though, as we mentioned, is also sampling images from the device. Again, this will only apply in certain customers' setups. Not everybody will ever want images from the device to ever be exported to the outside world. But we do imagine this workflow that allows what we call collectors to sample a subset of the predictions and send them back to the platform for iteration on the model. And eventually, what we would call active learning, where there might be some automated refinement of the models based on what's said. And now it's time for our demo. And I will show you our platform. And for this demo, we are going to use an AGX, an NVIDIA Jetson AGX device that we have synced some models over to from our platform. To start, we're going to log into the device from the command line here. I have this prepared so that I can SSH into the device, and I'm also port forwarding so that I can access, as I've described before, our platform is built on Kubernetes. So this will allow me to show you our Kubernetes cluster by exploring it with local commands through the port forward. And I'm also going to use the port forward to send some API requests to the device. Obviously, in the real world, we can have different setups for ingress, but for the purposes of this demo, we're just going to use SSH. Now, you might see here that the name of the device from my SSH config is Talon AGX. That is because we have a very hard-working team in Talon that has contributed so much to the Flare project. We really need to call out the contributions of them. And in fact, this device is sitting in Tallinn, Estonia. So hopefully the network won't give us too much trouble from where I sit in New Jersey. So here we've SSH'd onto the device. And this is an AGX device. And here, let me just cat from the proc tree structure. There's no new line at the end of this file, but you can see Jetson AGX. Okay, perfect. Taking advantage of this first port forward so that I can access the Kubernetes cluster from my local host. Let me clear here. I'm going to execute a kube control command. So I have my kube control context all set up. I'll use my keyboard shortcut just to make sure I'm on the right context for Kubernetes. Whoops, excuse me. Yes, so I have it set up on that context. And before we go any further, we can see cluster info that we are connected to the port forward. Okay, perfect. So if I look inside of the prod namespace of this cluster and I enumerate the pods, Kubernetes concept, you can see effectively the different processes and services that we're running. The exact deployment can change, and there are obviously, thicker edge deployments. Not everything is a device like an AGX. It might be a thick server somewhere, and there are thin deployments, and exactly what we run on it changes a little bit. But the point is you can explore the pods here. We have a logging solution to allow you to pipe the logs out of the device, but I can also just through Kubernetes explore the logs. So you can see the last 100 lines, for example, you can see this is just health checks happening, but this is of our API server. So that's the server, the process that is logically terminating the connections. Fine. So I have this set up, and I have this other port forward that I'm going to use to send an API request. So I have prepared over here Postman. Postman is a very useful tool for crafting HTTP requests. So this one is going to list the models on the device. And if you see the generated code here, you can see that this is I'm making a request to my port forward, which I have right here. And actually, while we do this, we can actually look at the logs on the device. So I'm going to tail the logs and follow them, just like so. And I'm going to use this Postman utility to send this API request that will this is just a GET request to list the models. So here we go. And with a little bit of latency because we are hopping across the ocean to Estonia through my SSH tunnel, but this enumerates a list of models on the device. And you can see logs related to my request here in the output. Wonderful. So let's make an actual predict. So for this is just a toy predict. I'm going to send it. This image is not actually representative of something that we would want to send to this model. So for this, I'm using the person vehicle model that we showed before. We will, in a moment, show how we can use that for video. But let me just open up a new window and show you. This is just a test image that I have of Metro North, if anyone's a New Yorker. This particular model isn't really trained on this type of data, so we might have some spurious detections. But we will, in a moment, apply a whole video that we hope to kind of show off. So let's, as we kind of mentioned before, I have here a Clarifai app with two different models in it. As we mentioned before, one of the major problems that we see is domain drift in models. Often, it's not even that the conditions are changing as a function of time, but rather just that the training set was distinct from the deployed domain, from the deployed images. So I'm going to click on one of the images that I added to this app, And I have a workflow over here that this is the first model that I had synced to the device. And let's just see the detections that it generates. Let me just reload the page. Oops, let's see. So this is an efficient debt workflow, and this is the same case that I showed earlier in the presentation. This model has many spurious detections, again, because this was trained on aerial footage, and it wasn't really intended for this type of footage. So, a classic problem. So using Clarifai apps, you can label and train new models. In this case, we are attempting to deploy to a thin edge device. So I want to be able to train models using or at least using the model architectures that people use for these small edge devices. That is a feature that is coming to the platform soon. Right now, you can do deep training and transfer learning in our platform. And those models that you deep train and transfer learn, you can, of course, use with Flare, but many of them as they stand right now would be better suited for a thicker edge device. If you want to import your own highly optimized model, you can, which is exactly what we did here. So again, we're not quite there yet with the launch for training with an appropriate template to generate a YOLO model, but I have one that I've imported here. For thicker edge devices, this doesn't really matter. The deep train models that we do on the platform will export just fine to them, as will any of the transfer learn models. And you can see that I've found a model that performs much better. This lacks many of these spurious detections. And I want to try this out on the device. Now, again, Clarifai offers a whole suite of tools related to training. I have another app over here where I actually did train a model. This is actually a transfer learn model to detect different types of professional people. And I can look at this model that I trained, and you can see all types of evaluations related to the training, whether it's a confusion matrix or recall, etc. So I can similarly, you can bring the power of these evals to the models that you import. That's a feature that we will be launching soon. Again, having seen the improvement of this, I want to try this improved model on my device. So I've synced this model to the device, and now I want to send a request to this new model type, and we need something interesting to do this with. So I have dug up some videos that are similarly out of the domain of where the efficient. I'm sorry for the audio. Let's turn this down. So this is kind of just a street view from London. And this is something that clearly this YOLO V5 model might do better on, whereas the efficient debt model that I showed before with all the spurious detections similarly would not do very well on this input. So having synced the new model to the device, I'm now going to copy this video over. So let me do that now. Let's actually open up a new terminal here. Project Flare. And I can, so I have the video prepared right in here. And it's this one that I want to copy over. So let me SCP this over to the device. I'm SCPing it to the device simply because the device is in Tallinn and I don't want to deal with the additional round trip latency related to my SSH tunnel. Here we go. So SCP of this guy to our Tallinn AGX. And I'm going to put it into a directory that there we go. Let me just double check the correct directory. Visualization. Okay, yes. So I think I got that right. Sorry. That is a typo. So we are SCPing this over. And I've prepared a script that, again, I've placed on the device. As you can see, there's many different ways that you could do ingress. Before we made these requests through the SSH port forward. And in this case, now I'm actually going to run this script. Let's see if I have, yes, I got it. And now I'm going to run this script directly on the device. So you can imagine another use case where you might have another process on the device that is feeding the API. So I'm going to run this visualizer. So you can see it's a little script that I put together. And it'll just print out some of the options. Let's just invoke it with, let's increase the frame rate that we're going to sample the video to from the default to 10. And let me pass the video. And here we go. We are going to cut to the end here. Right now, FFmpeg is decoding the video. Actually, we'll just wait until FFmpeg finishes decoding and starts to send the request. This is just how I set up my silly little script here. And you can see it's starting to send requests. And here where we're tailing the output, you can see that it's getting the request. This is just a simple single-threaded approach to sending the requests. And with that, we will leave you, and I'll be joining you with the finished product in a second so that you don't have to wait. Okay, welcome back. So the test has now, the script rather has now completed, and it has generated this output file for me, and test.mp4. And so now I'm going to jump over here to this other tab, actually this one rather, and let me cd to this video out directory where I've been storing these, and let's scp this output back. So scp, and let's take the same directory as before, but now we want to grab this file and test.mp4. And let's put it here, and let's call it test3.mp4. I'm not sure. Yes, perfect. And there you go. Apologize for the slow connection here. Technical difficulties, of course, but here we go. And we can see the output over here, and we can now watch the video. And I can already see, let me make this as large as possible, some bounding boxes here, and they look quite accurate to me. Very good. You see tracking the different people, or actually these are just detections. We could add tracking to the workflow so that we could add a track ID to each person so that you can track between frames. And I would say this is quite the success. So very good. I hope that you guys have enjoyed this talk. And we hope to get this in your hands very soon. And enjoy the rest of the presentations. Bye-bye.